All right, so let's come back. So we got a little bit less than half hour for the afternoon lecture. I hope I didn't give too many equations to you guys. A few equations was quite simple linear algebraic stuff. Hopefully we can just focus mostly on the physical meaning for those terms, and because it's really some very useful tools you can use to do diagnostics of your flame, so you can understand what happens there. For this turning, therefore, we identified the two important time scales, one for chemistry, one for mixing. The mixing time, we know basically at the turning point, extinction point. So chemistry become, the time scale of chemistry become balanced by the time scale of loss. And then that'll give you a so-called Dunkel number equal to 1. If you want to define a local Dunkel number based on the mixing time scale versus chemical time scale, and you know this tau s, tau omega is just the reciprocal of the eigenvalue contribution. Okay, so tau s is 1 over lambda s. So tau omega is 1 over lambda omega. In that case, you can pinpoint which time scale in chemistry actually causes extinction. If you want, you can further dig into who or which reaction is contributing mostly this chemistry part of the eigenvalue. So let's see what we can get from this. So first of all, before we look at other information, we want to show you the lambda omega. So basically, I use different terminology, but this is the lambda omega along the S curve. Okay, if you look at the extinction state, so on the upper branch, if you look at chemistry, because it's strongly burning, you get mostly a product, although temperature is high. Because you have a mostly product, the mixture is not explosive at all. It's no explosive behavior. It's approaching equilibrium. It's like this kind of behavior. Okay, approaching equilibrium. But if you push the system to the turning point, you see close to the turning point, the system becomes explosive. One of the chemical eigenvalue become positive. That means the mixture become explosive, right? You get enough reactant remaining there. So it reaches most explosive state somewhere else, but at this turning point, this lambda omega happens to be balanced by the time scale for mixing, and that's when the game changes. So around this point, so chemistry fails, and then the system can be pulled down to the lower point. Okay. So this is what happens if you put these two terms together. So if we put lambda omega, let me see. If you put a lambda omega minus 1 over tau. By the way, tau is residence time for PSR. And we said because PSR, the mixing is only have one time scale for mixing, which is the residence time itself. All the scalars, different species, temperature, the mixing time is the same. So therefore, the Jacobian for mixing in PSR is approximately diagonal matrix. Each eigenvalue is 1 over tau. So therefore, lambda s, this is lambda s. Okay. So therefore, if you put this lambda omega plus lambda s in this curve, you can clearly see this gives you zero crossing on the two turning points. So that's indeed tell you the competition between chemistry and mixing. It gives you the extinction or ignition behavior in the steady state combustion systems. And then if you look at the S curve for different fields, for methane, it looks like exactly what we plotted in the previous canonical S curve, right? So a simple S curve, upper branch, middle branch, lower branch. But if you look at DME air or whatever real engine fuels, you find the S curve is quite complicated. You get a lot more turnings. Again, the upper branch is still the extinction state for strong flame. If you get strongly burning flame, the chemistry is still the same, controlling the large hydrocarbon fuels or DME. But the lower branch this branch is additional to the large field. If you get NTC chemistry, you get a cool flame branch, and this branch can be stable. Not all of the portion, but part of the portion can be stable. Okay, this lower branch this is the unburning part. So you can see this is middle branch, this is the middle branch. You get two middle branch in these cases. upper branch is for strongly burning flame, and this is for a cool flame. So the S-curve for engine fuels can be a little bit more complicated. Sometimes you get even more turnings, more than just 1, 2, 3, 4, 5 wiggles. You gotta get a 6, 7. But whatever. Anytime you look at the turning point, the math is the same. Okay. But then you can probably look further into the eigenvalue, because the eigenvalue, in some scenario, eigenvalue can be real numbers. Sometimes eigenvalue can be complex numbers. If it's a complex number, the real part of the complex number, it determines whether the system is grow or decay. If you get a positive real part, you get explosive behavior. Negative real part, you get decaying behavior. But the complex part tell you oscillatory behaviors. Okay, so complex number nothing big deal. It tells you something oscillates. You look at the real part, whether it's positive or negative. It tells you whether you get an explosive system or you get a near equilibrium decaying system. Okay, so if we look at the real part of the system, we find these blue segments, you get all negative real parts. All the eigenvalues has negative real parts. Means it's stable. It's stable. But the dashed parts means at least some 1 or 2 eigenvalues you get positive real parts. So then, if you get any positive real part, the system is not stable. So that means for this particular case, for DME, it's not getting unstable actually exactly at the turning point, but rather before you reach the turning point, the system is already unstable. So extinction can occur crossing this point in real systems. So therefore, we don't just put too much belief into the turning point. Sometimes we call the turning point to be extinction point, but in real flames, sometimes extinction happens before you reach the turning point. Okay, and whether you can figure this out, it depends on, you have to perform the eigen analysis based on the Jacobian matrix. That's why we see the Jacobian matrix is so important. It's critical. Okay, so sometimes flame extinction can occur away from the turning point. Okay? Sometimes it's at the turning point, but you do need to look at the Jacobian before you can determine it. All right, so this is something we can learn from this. And if you want to drill down further to figure out which reactions are controlling the extinction state, because you want to get a reduced model, right? If this reaction is controlling the extinction, flame extinction, that's probably the reaction you want to retain in your reduced model, right? How can you figure out which reactions are important for the extinction? Then we can dig into this chemical Jacobian. We know the Jacobian can be decomposed into 2 parts, the chemical Jacobian plus the mixing Jacobian, right? And the Jacobian of chemistry can be further decomposed to the Jacobian of each individual reaction. Because omega, let me just write here, omega is equal to sigma omega I, as I did before. So the reaction source term is attributed to the summation for all different reactions put together. Okay, you do d omega dy, you get a sigma d omega r dy. So the GR is a contribution for the Jacobian from each individual reaction. Okay, so similarly, if you do the eigen projection to the full Jacobian, you can decompose this chemical part to the summation of contribution from each individual reaction. If this lambda r is significant, that reaction is important at the extinction point. If this lambda r is negligible, it doesn't play an important role. It's not controlling the extinction state. All right. So if you normalize this contribution from each reaction, but normalizing by the maximum term among all the reactions, so we call this a bifurcation index. It tells you which reaction is most important at the extinction. Then you can give a rank. And this rank is somewhat comparable or similar to what you can get from sensitivity analysis. You can do perturbation of reaction parameters and get which reactions are important for extinction, but then you need to do a lot of iterative runs. But this one you can directly drill down, just explicitly get a formula. So let's look at this point, E2 prime. E2 prime, this is extinction for strong flame. This is extinction for cool flame. By the way, This is stable branch for strong flame. This is the stable branch for cool flame. You can run your engine here or here or here, but just not in the dashed line regimes. Okay, but if you look at which reactions controlling this point, by rank all the bifurcation index for these reactions here, you can see clearly this is seal formation, right? This is seal formation. This is the two most important reactions are related to seal formation, and they are simple. One, if you look at the sign, they are different, opposite sign. Why? Because one is endothermic, one is exothermic. So this one, it has oxygen involved, so it's exothermic. This one, through a third body collision, is endothermic. So it gives it different effects. One promotes, so this one promotes burning. This one prohibits burning, and therefore they give you different. And the competition between these two fight with mixing to determine the extinction. So therefore, for this particular case, you can see this is a rich case, by the way. The formation for seal is the guy who fights with mixing at this location. Okay. Yeah.
Does this relate to the time? For example, you have an initial time step and you will go on calculation.
So your question is this result relevant to different time? To clarify, this is a stirred reactor, steady state stirred reactor. So it's not an unsteady stirred reactor. If you have an unsteady reactor, you can possibly have oscillation behavior, whatever. But this is steady state solution, and this S curve is a typical response for steady state systems. So that means on each condition, each resonant time, you can have different possible solutions. It depends on where your system is initialized. It either stay there or jump around. So it depends on the different condition.
That means your mixing is constant. Your mixing time.
Right, you're saying if the mixing, because I need to repeat this for the recording purpose. So you ask whether this is for fixed residence time. Yes, for each fixed residence time or fixed flow rate, you can get a possibly different solutions. So sometimes, imagine if you get a flow going on, sometimes you don't have flame. You just don't have flame forever. You can run this forever. Sometimes you have flame running, you have the burning running forever. So it depends on where the system is initially located at. Okay. So, and this one tells you, if you look at extinction for cool flame, which reactions are important there, controlling the extinction for cool flame, you clearly see the mixing is here. So you get three reactions competing with each other, right? So all of them are what you are familiar with. If you are working on NTC chemistry or this low temperature chemistry, you are familiar with the peroxides, right? So this is OOH. This is the peroxide. So all of them are some kind of this chain branching steps at low temperatures. All right. So you see this NTC chemistry fight with mixing, give you the extinction for cool flame. So therefore, they indeed give you the relevant reaction. And if you want to run this ignition case, you will find ignition cases are controlled by totally different set of reactions. And also, the controlling reactions here, each different turning point or bifurcation point, you get a almost completely different set of reactions, very different set of reactions. You do have some overlaps. For example, H plus O2, that can appear in different turnings, but you get a very different set of reactions. So that means if you only reduce your model at this location, and it may not work for here, but if you want your reduced model to be valid for all different kind of different flames, you do need to sample for different scenarios around this turning. So you do need to include those sampling states. Okay. Yeah. Question.
I noticed that this is for equivalence ratio 5. Is there an indication of how the S shape will change with different equivalence ratios? Is there like a rule of thumb, or is it specific to it?
That's a good question. So you are asking, this is a phi is equal to 5, very rich case. The reason why we use a rich case is because this S curve looks more prominent at phi is 5. At the link case or stock chemistry case, it still looks like this, but this wiggle is not that prominent. It's a little bit shrink backward. you can see a large turning here and then a small cool flame turning. But it depends on the situation. The shape of the S-curve looks slightly different. I think I have it somewhere else for DME S-curve.
So just as a follow-up, it's better to calibrate our models in higher field in terms of like.
Oh no. You meant if we want to get a reduced model from PSR, should we use rich cases? No, this case is only used to demonstrate two purposes. One is the extinction point may not be the turning point. That's the first one. It occurs clearly for this rich case, but not for link cases. For link cases, we find they are the same. Okay. Secondly, this one it shows you that clearly there are two major branches. You can have strong flame extinction, cool flame extinction. For link cases, you get sometimes you get a good cool flame branch. Sometimes you get a very small short section there. So, but whether you should use rich case, you should look at your flame. If you are dealing with lean flame, you sample from lean stir reactor S-curve. If you are dealing with rich flame, you sample from rich reactors. Yeah, the actual parameter here, pressure, temperature, the feed, it should depend on the parameter range you want to cover in the reduction. All right. Yeah.
Hey, another question. You always make assumption this is for ideal reactor, right? But it is rarely to apply to the CFD application when you analyze this one. When like how to determine the mixing time when CFD acidity in your PD equation?
Yeah, that's a good question. So you asked if we do reduction based on this idealized reactor, 0D reactor, it may not be exactly the same condition as the competition we saw in turbulent flames, right? Yeah, that's a good question. But the thing here, if we look at this location, their reaction pathways are dramatically different, largely different. So you do need to keep these different families of reactions in the reduced model to capture these two different very different reactor types, okay? But in real simulations, you will find actually in turbulent flame, you will often find sometimes auto-ignition controls the burning. Sometimes it's forced ignition by mixing product with the fresh mixture, it controls burning. For both scenarios, actually, it's quite typically represented by these two different scenarios. These two scenarios, it don't have to be exactly have the same concentration for the reaction pathways to be retained. You know, your competition can be off a little bit with some kind of range, but as long as you are in this regime, this set of reactions are retained, then that's fine. It's almost not possible if you want to get exactly the same set of reaction compositions from turbulent flame, unless you do the simulations in advance. But if you cannot do it, the best we can do is we try to choose the several different types of 0D or 1D reactor, which is most representative to the bulk phenomena, the bulk types of phenomena, which you can possibly have in your flame.
Yeah, that's my say. If you run CFD, you can use this new method to analyze your result.
Right.
CFD simulation. That's what.
Oh, right. For whatever model, if you get a model around this, so your question is, if you get a reduced model here, you can possibly use this reduced model to simulate some kind of a turbulent flame around this regime, right? This is possible because whatever reduced model you get from here is not only valid for this point, because keep in mind, this model will be valid for some kind of reasonable range. This range, as long as the major set of controlling reaction pathways are there, there is quite a good range you can extend it to. So typically you get an extinction problem, it can cover, if you get a reduced model around it, it can cover a large range from here to here, even to the middle portion of this. So the reduced model is not valid only for one point. So fortunately, that's the case. To verify this case, you can easily do the reduction for some cases, and then you choose some different cases you try. The chances, it's a very good chance you can extend this to very different flame types. For example, you get a reduced model from a stir reactor. Almost always we find the laminar flame speed is right in that case. So whether with stretch rate or without stretch rate. So the flame speed is right. And also for turbulent combustion, for different color width numbers, you find the flame structures make a lot of sense actually, because actually, although the flame structure can be very complicated, the controlling chemistry is not that complicated. Particularly for turbulent flames, because you try to mix different people, right? Some high temperature mixture with low temperature mixture, when you mix them, this guy try to force ignite the other one, but the other one takes some energy from his party. But this is this one story is two sides. So extinction or forced ignition is the one story, but two different sides. It's to make another analogy. It's just I always try to use this analogy to explain this behavior. Auto-ignition is to build up radical pool, okay, or to release heat. It's just like we want to make money. If we have $1, we work hard for 1 year. Next year it become $2. You keep on this doubling. Maybe 20, 30 years later you become rich, right? So this period is 30 years you need to take for the radical explosion. This time is your ignition delay time. But if your parents give you some money to inherit, you can become rich overnight. So within one day, a few days time, you can bypass this fortune accumulation period. Just quickly become somebody which can manage a large amount of money. You can become millionaire or billionaire very quickly. Okay, so in turbulent combustion, you don't want everybody to start from scratch to build up radical pool by yourself. You want to mix different people. That's why mixing is so important in turbulent flame. You try to mix as hard as possible, so rich people get a chance to see poor people and to exchange money. You know, some scenarios, rich people get extinguished. His money was taken away by many poor guys. That's the extinction. Okay, but his money will never be wasted, because when those guys get money, a few times later, it can become rich very fast. Overall, the burning rate can be enhanced by this massaging process. You just bring people together. In learning, we also do the same thing. You know, that's why we have schools, right? We have the senior guys, we have junior guys. If every junior guy learn everything from the beginning, we are doing auto-ignition. It takes maybe 30 years you can learn what S curve is. But if you take the class, now, you know, after this today, you pretty much bypass a lot of elementary stuff. You're boosted to a different level. So this is what we learn from this real combustion system. It's a lot of similar scenario in our life. You know, particularly in combustor design. If you want it to burn fast, try to mix different stuff, whether through a recirculation zone or through a stir device. Sometimes you put a fan or whatever to just stir it. Whatever way you can use, try to mix this different stuff. It can enhance the burning. That's the reason. It just bypass the slow auto-ignition process needed for a radical explosion. Okay. So therefore, in turbulent flame, don't be scared about this complicated flame structure. So there are two major types of, let's see, use the example of premix flame. The flammable regime is similar to 1D laminar flame. Okay, if you can use PSR to get a reduced amount of 1D flame, it works quite well for flammable regime. But for strongly turbulent flame, you get a broken reaction zones, you get local extinction, reignition, but it's close to stir reactor type, somewhere scattered around the turning point. Okay, in that case, if you can get a reduced model which works well, it actually captures the majority of the physics for these highly turbulent flames. So in this sense, a lot of cases you see seemingly complex scenarios, but some of the process or some of the physics behind it can be rather simple actually. Okay, so fortunately for model reduction, we have this blessing, and we don't need to sample from real turbulent flames to make everything working. Fortunately. Okay. I get a few more minutes. Maybe we just stop here. So skeletal reduction is a whole lot of interesting stuff. Well, we will keep on looking at different methods for skeletal reduction, time scale based reduction tomorrow afternoon. Okay. I guess it's enough torturing for you guys in the late afternoon. Thank you for still being awake. Okay. All right. Thank you very much, guys.